Hello. Today we will be going over question 3.3a of the Heat and Mass Transfer 8th edition. Uh, this one is specifically touching on thermal circuits, so we will be going over how to do that specifically with this problem. On the right is the actual stated problem from the textbook. So it reads, the rear window of an automobile is defogged by passing warm air over its inner surface. So specifically, we will be working on part A, which says if the warm air is at T infinity, I equals 40 degrees Celsius, and the corresponding convection coefficient is H equals around 30 watts per meter squared Kelvin, what are the inner and outer surface temperatures of 4 millimeter thick window glass, as well as it gives us the outside ambient temperature being negative 10 degrees Celsius and a convection coefficient of 65 watts per meter squared Kelvin. So over on the left hand side is my worked out problem. So we'll be going from through this now. So as you can see, I've followed the normal homework pattern where we provide what we are given and what we need to find, schematic and so on. So starting at the top, once again, I just wrote down the given details. So TI is 40 degrees Celsius, HI is 30 degrees, TO is negative 10, and then HO is 65, and then the thickness of 4 millimeters. We need to find the inner and outer surfaces, or surface temperatures of the glass. So here in my schematic, I have labeled the outside, the inside, and in this rectangular box right here is representative of the glass. Specifically, its thickness is given here in its dimensions. So here I drew that TO is going to be down here, and then TI will be here. This will make more sense later as we go through the problem. And then I just have a regular coordinate system here. Um, so to represent that it's convection, I have drawn little clouds over here that represent the HO and TO, as well as inside HI and TI. So starting off with some assumptions, what you can make is that there are constant properties. There's no changing factors in this question. It's not specifically saying different uh, temperatures or different heat coefficients at certain points. So we could say that there's constant properties, especially with like the material as well. That's not changing, so we could just keep those at a constant state. Additionally, we have no heat generation. Since we were given temperatures and heat coefficients, we could just assume that there's no heat generation, especially in the glass. That wouldn't make too much sense. It doesn't specifically say anything about heat generation, so we don't have to worry about it. I've also stated that radial effects are negligible. My assumption here is just um, small a small object in a large space. So we could just assume that radial effects are going to be very small in this question, so we can neglect those. It also makes it easier for us to solve the problem. In the problem statement, we were given that it's a window, so assuming glass. Since it did not give us any properties of that, we would have to tap into table A3 of our textbook, and in there we could find that we have a thermal uh, conductivity coefficient of around 1.4 watts per meters Kelvin. So we will be using that for this example. We could also assume that this is a steady state problem. They didn't give us any initial temperatures or any time dependent variables, so we could just go ahead and solve this as a steady state problem. And then finally, we can neglect contact resistance. Normally, you want to do this because it overcomplicates problems. And additionally, there are not multiple solid surfaces touching, so there's no worry about contact resistance there. So, hopping into the analysis, we can see that I have drawn the thermal circuit for this question. So starting in the outside area, we have T infinity O, which then hops in to some convection, which we have labeled as R convection O. And then now first hit temperature of the outside layer here. You can see it matches up with the drawing. Following that, we have conduction through the material. So that has been labeled with R conduction. which is then going to lead to Ti, which is the temperature on the inside layer. And then finally, again, we're going to be hitting some convection with the inside of the vehicle and those corresponding values. So a great way to start this problem is if you don't know certain temperatures on the in between layers of this question, you could solve for the entire heat flux according to your starting temperatures. So the inside and outside, we can use those two temperatures as the temperature difference and just incorporate the conduction or the convection, the conduction, and then the outside convection again, and we can find what that heat flux is. And then from there, we can use that heat flux to solve for any internal temperatures that we were looking for. So in this case, we could use it to solve for TO and TI. So that is exactly what I did here. So you'll see that we have the heat flux of the entire equation. We have the difference of temperature being T infinity I, so the internal temperature of 40 degrees Celsius, minus the outside temperature of negative 10 degrees Celsius. And we also incorporate those layers of the thermal circuit. So we have our convection outside, we have the conduction through the glass, and we have our convection inside. Now, when using heat flux instead of just heat, we can then neglect area and just focus on more of the convection coefficients, the conduction coefficient, and also just the thickness of the layer that we were trying to solve. This is going to help us because the problem did not give us any other area dependencies or surface area of the glass. So a breakdown of the equation again. So we have the temperature difference as stated before, but now we have the actual values that we need to place inside of these equations. So as you can see, our convection of the outside turns into 1 over HO. So that is going to be being replaced by the 65 watts per meter squared Kelvin. The thickness over K is your conduction value, the resistance. So we are going to put the 4 millimeters, or in this case, 0.004 meters, to ensure that we have the correct units, over the thermal conductivity coefficient that we found, which is 1.4 watts per meters Kelvin. And then finally, we're just going to do the same thing for the inside as we did for the outside. So that's going to be 1 over 30. So here we are changing these values into Kelvin just to ensure that the units all cancel out correctly. So you just have to make sure you take the difference of these values and then go ahead and solve for this, and then you'll finally get your final value for your heat flux of around 969.46 watts per meter squared. So from this, you can then use the value to break down into smaller components to find your TO and TI. So following that, I started with TI, and we can use the same Q because it is a steady state condition. So following that, for just finding TI, we will be using just the convection is the only concern here. So we have T infinity I, the internal temperature of the vehicle, minus Ti, the first layer of the glass, divided by your R convection internal coefficient. So we have 1 over Hi. So following this, we don't know what Ti is yet. We do know what the internal temperature is, the 40 degrees Celsius plus 273, which gives us the 313 Kelvin, and over the 1 over 30 watts per meter squared Kelvin, all equal to that 969.46 value that we found earlier. So some simple algebra and everything turns out to make the temperature of the internal layer being around 280 degrees Kelvin, or more specifically 7.68 degrees Celsius. And then following suit, we could do the same exact thing for the outside temperature. So for here, or yeah, the temperature of the outside layer of the glass. So here we can use, once again, the heat flux that we've found before. And then for our temperature difference, now it is T infinity I minus T outside layer. So with that, we will need to both incorporate the convection here and then the conduction as well. So that will be the two components of our circuit. So as you can see here, I did just that, 1 over the HI, the same as before, but now we are adding that conduction uh, resistance. So here we will have to incorporate the thickness again and then the K value, which you can then see I provided here. So we don't know what TO is. We are solving for that. You just input all your values like we did before, and then you find that TO is going to be equal to 277 Kelvin, or around 4.91 degrees Celsius. So, back to the drawing. Specifically, I drew TO and TI at this points to show the linear progression of heat, or the temperature change. So we knew that TI was going to be warmer because the inside temperature is the closest to it. So it'll be a little bit more warmer inside than it will be outside, obviously. And the math backs that up exactly. So TI was greater than TO by around 3 degrees Celsius. This makes sense because that external temperature is pretty harsh. So you're not going to see a great difference in temperature, especially between something so thin of around 4 millimeters. So yeah, um, this is the end of the problem. Thank you for listening, and I hope this helps you out.